Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are continuing the topic discussed in last two lectures. The topic is, let me write, enumeration of modes density of states of a continuous medium. Right here, continued. So we're continuing with that topic. Let me underline it. In the last lecture, we reached to this equation. We got actually this quantity v by 2 pi whole cube 4 pi q square dq, and we named it equation 13 in the last lecture, second lecture of this topic. This third one pertaining to this topic, density of states of a continuous medium. In the last lecture, that is second lecture, we named this equation as equation 13. Then I lost my internet connection. I couldn't complete it in that lecture. Hopefully in this lecture, we will conclude this topic. You know, V is the volume of the sample. Actually, what we are trying to do, we solved for the density of states function for one-dimensional case. Now we are trying to find the same function for three-dimensional case. For that, in the last lecture, as you know, we, for simplicity, considered a cubic sample of edge length L. This V is the volume of the sample. Q, you know, is the wave number. Then in the last lecture, we said this number, this quantity, this V by 2 pi cube, 4 pi q square dq, which we got by differentiating the equation 12 in last lecture with respect to q. We said this particular equation gives us what? It gives us number of modes or points, because each point in Q space is representing a mode of vibration. So this is the number of modes or points in the spherical shell between the radii Q and Q plus dq in figure 4 of last lecture. That is second lecture of this particular topic. I will roughly draw that figure. This was our figure 4 in the last lecture. This is QY, this is QX, and then we drew it like this. I will draw it roughly and go to last lecture to understand it. Then use another color. This was my origin, and we took the radius of this inner circle as q, and this was omega contour. Outer one was omega plus d omega contour, and this was d omega. Remember, it is this figure 4 is showing what? It is showing allowed values of q, which is now a vector in 3 dimensions for a wave traveling in 3 dimensions. And in this figure, only cross section is shown in qx, qy plane. Now the shaded this one, let me shade it with another color. The shaded circular shell is used for counting the modes. So this was our figure. Let me chuck it, omega contour, omega plus d omega contour. Now we are saying this thing is representing the number of modes or points in the spherical shell between the radii q and q plus dq. That means number of modes available in this shell. The shell shown in this figure 4. Why so? Because as you see, v by 2 pi cube is giving us what? Number of modes per unit volume of q. And 4 pi q square dq is just the volume of this shell. So when we multiply these two things, we get the number of modes or points in the spherical shell between the radii q and q plus dq. So let us move forward. As you know, the density of states is defined now. The density of states g of omega is defined such that g omega d omega is the number of modes, is the number of modes whose frequencies lie in the interval omega and omega plus d omega. So this number may be let me write it this way. This number can be obtained from equation 13, or I should write from 13. This thing by making a change of variable from q to omega, as they are related through dispersion relation. So I should write by using the dispersion relation. What is that relation? Relation is, as we have discussed in last lectures, omega is Vs times Q. Using this, we get d omega is V by 2 pi whole cube times 4 pi times omega by Vs whole square d omega over Vs, right? G omega d omega is V by 2 pi whole cube 4 pi times omega by Vs square times d omega by Vs. So you can see it is this thing. V by 2 pi whole cube is same. 4 pi is there. We are replacing Q square from this dispersion relation by omega by Vs square. Then we are replacing dq by d omega by Vs by making use of the dispersion relation. Now this expression gives the number of points. As you know, this expression gives the number of points between the surface of constant frequency at omega and a similar one at omega plus d omega. Now plotted in the Q space, these surfaces are spheres, as you know from this figure 4. And the volume between them is the spherical shell shown in this figure 4, right? Now the above expression for the above expression, for g omega d omega is the number of points inside the shell. The shell shown in the figure. This shell, right? This one. So according to above equation, this equation, the density of states is thus given by, therefore g of omega is V over 2 pi square omega square by Vs cube. the name it equation, this was 13, this is our 14 equation. Let me encircle it. So g of omega is v by 2 pi square omega square by vs cube. This is just simply this expression. We have just cut this d omega in the left hand and right hand side. We have cancelled it. We got v by 2 pi cube. Then we adjusted this 4 pi and 2 pi cube. So we got this v by 2 pi square omega square over vs cube. Now this function we can plot. This function is plotted versus omega in figure 5. Let me draw this figure. So if you plot g of omega versus omega given by this equation, this is my figure 5. Which equation? Equation 14. You get the parabola, right? So we are plotting this density of status given by equation 14 versus omega. As you see in this equation 14, g of omega is related with omega square. So g of omega increases as omega square, unlike the one-dimensional case. So let me note it here. G of omega increases as omega square, unlike the one-dimensional case, in which, as you know, g omega, in which g omega was a constant, right? You can see it in the previous lecture. Now, the increase in the present case is a reflection of the fact that the volume of the spherical shell in figure 4, this figure, increases as q square, right? And hence as omega square, since omega is proportional to q. I repeat, the increase in the present case is a reflection of the fact that the volume of the spherical shell, which is this, and circle it, increases as omega square, as you see, and hence as omega square, since omega is proportional to q from dispersion relation. Omega is proportional to q, right? Now, one last modification which is necessary. So one last, let me get my pen back. Okay. One last modification to this equation. What is that? Which is necessary. Now, in the above discussion, we have associated a single mode with each value of q, right? We have associated a single mode with each value of q. This is not quite true for the three-dimensional case, however, because for each q, the wave may be either longitudinal or transverse. For each q, the wave may be either either longitudinal or transverse, right? So there are actually three different modes. We write it in red. There are actually three different modes. One longitudinal and two transverse. Associated with the same value of q. The dispersion relations for the longitudinal and transverse waves are different. Remember, the dispersion relations for the longitudinal and transverse waves are different since they have different velocities. But if we ignore this difference and assume a common velocity, we obtain the total density of states from equation 14 by simply multiplying it by a factor of 3. That is, g of omega is 3v by 2 pi square omega square by vs cubed. This is my equation 15. Let me encircle it. G of omega is 3v by 2 pi square times omega square by vs cube. We have simply multiplied equation 14 by a factor of 3. This equation. Right? So we have obtained ultimately the density of states function for three-dimensional case, which is 3v by 2 pi square omega square by vs cube. V is volume of the sample, omega you know is the frequency, and vs is the velocity of the wave. But you need to remember in this expression, but we are doing what? We are assuming a common velocity, assuming a common velocity for longitudinal and transverse waves. for longitudinal and transverse waves. We're assuming common velocity from them, which is not correct because displacement relations for the longitudinal and transverse waves are different. They have different velocities. We're ignoring this difference in this expression and multiplying just by 3 and to get the total density of states. Now we will see in the next lecture that we will use this formula in connection with the Debye theory of Debye theory of specific heat. Note that G omega is proportional to V, the volume of the specimen, as you can see from equation 15. We shall often conveniently omit this factor by taking our volume to be equal to unity. If you take volume equal to 1, V will disappear in equation 15, right? So this is all for today. Prepare your exams, don't waste your time, and don't forget to like and subscribe my channel. You can comment in the comment box. Thank you. God bless you. Assalamu alaikum.